temperature extremes, etc., can be solved with building of a greenhouse, which would architecturally probably pre-exist any crops or people on Mars, assuming that. But one problem that we came across that we weren't quite sure how to solve immediately was the toxic contaminants in the soil. Now, normally with Earth soil, there is some variation, and there are metals and such, but due to the lack of research and lack of precision in the research done on Mars, we don't have that much data to cover the toxic contaminants, such as metals and perchlorates. We do know that perchlorates and sulfates are in the Martian soil, but we don't know the amount. And some of the elements listed at the bottom here are found in the Martian soil. We don't know how much, but we will assume that there's a high likelihood of high toxicity rates. And these pose the greatest threat to Martian endeavors and agricultural endeavors on Mars because, like with anything, too much can kill you. So we are assuming there are unsafe human ingestion levels because, there are some, excuse me, but on let's just say in the movie or the book, The Martian, I'm assuming, have you both read it? Yeah. It was a good book, right? It was an excellent book. However, one problem that Andy Weir did not address was toxic contaminants in the soil. And if he addressed that, Mark Watney probably would have died within the first 3 months of consuming that much lead, that much cadmium, that much chromium, that much copper, that much barium, and then he would have nobody to bury him, per se. So, at an unsafe level, these can cause problems such as skin discoloration. They're probably past the emetic threshold, which is the threshold that allows you to upchuck. And yes, so why we are assuming this is because NASA's top priority has always been the safety of its astronauts, correct?
Mm-hmm.
Yes. So with that in mind, we would like to present the rest of our experiment to you, in which my colleague Trent will discuss our solution, which is phytoremediation.
Okay, so phytoremediation. So phytoremediation is basically just using plants to extract certain contaminants from the soil, such as organic compounds, inorganic compounds, and even just other generally bad pollutants that are maybe in soils. And so we actually know this is work because there's been several examples where they actually end up using it and successfully, such as one in Tyndall Air Force Base in Panama City, where they ended up using plants to extract perchlorates. One of them was actually carried on, which we'll talk about later. And so we're looking at the subcategory of phytoremediation of phytoextraction. And so phytoextraction is using plants again to extract the materials and store them in their stems, where they can be easily removed and then disposed of. And so we have a word for a certain plant that's able to extract a lot more than other types of plants, and that's hyperaccumulator. And so hyperaccumulators are able to store and extract a lot more contaminants than other plants and faster. So our next thing is up to Donovan.
So in order to grow these plants, the hyperaccumulators, we need to have a knowledge of what the soil composition would be. Just like growing your normal garden, you need to know sort of if it's loam, sandy, just the different specifications of your growing environment. On Mars, this is a bit of a different problem because the only instruments that we've sent that have to deal with mineralogy and geology are more concerned with the formation of these sediments. The Curiosity rover contained the ChemIn instrument and the alpha spectrometer, and these were capable of measuring the concentrations of various elements in the soil. However, it was only accurate up to 0.1%. And while 0.1% doesn't seem like a very large amount, when dealing with plants and other biological systems, that 0.1% could possibly be lethal. So in order to address this, we are trying to get as close to the Martian soil as possible. As you know, there's never been a Mars soil capture mission. So we don't have the actual tools that we would use to analyze soil on Earth. We would probably use chemicals, other large instruments, but we can't do that on a small rover where cost and weight are extremely key. So what we do have is the JSC-1 Mars simulant and the MMS simulant, the Mojave Mars simulant. And both of these provide very good, as their name, simulants of what the Mars environment would be. And we actually have samples for you today, just so you can see.
Would you like to describe the type?
Sure, so we have both coarse and fine samples for you to see. And they both are similar to the Martian soil, but since Earth and Mars are so different geologically, they don't, what's important is that they don't contain the same micronutrient environment that might exist on Mars. And especially, they don't contain the sulfates or perchlorates that we actually know do exist in Mars and possibly a contaminant, in a possibly lethal amount. And so, in order to test whether we can use phytoremediation on Mars, we've developed an experiment to lay the foundation of our understanding of this technology.
So our experiment is basically going to identify which of the phytoremediators do what, and then which order we should use them in, so that we can successfully remove all the contaminants, or most of the contaminants from the soil to make them edible for humans, hopefully to colonize Mars. So in order to do this, our independent variable would be the type of phytoremediator that we use, and then the dependent variable would be the amount of contaminants left in our control crop after we do a growth cycle. And so one problem that we might run into that Donovan sort of addressed is that the simulants that we have, they don't contain exactly what we might expect to be in the Martian soil. So one way we can address this is to basically add different levels of contaminants into the simulants in order to replicate the worst possible case scenario we might run into. And so while this is just the general idea, we can go more in depth with our process and procedure.
Okay, so this is a rough flowchart of our procedure. As you can see, it's quite repetitive, and there are many. It seems like there are many steps that are repeated throughout the course of the procedure. But as you can see, there is a slight change in there, and that is because when you're starting the first cycle, we're going to grow all the different plants individually, so that as to get an understanding of how effective they are in each situation. During the growth process, we can observe their growth and monitor how well they grow in the different contaminated environments. And when we're done, we'll end up with a set of plants that are probably all quite ill with the amount of contaminants that are put in there. So, but from that soil, we can then grow the control crop, which would be the prospective food crop that we're going to send to Mars. So, I think potatoes potatoes and tomatoes are some of the ones, but it could be any consistent crop that we're going to grow in the soil. And then from there, we can analyze how that control crop grows, so as to see what the change in the toxicity of the food, and the end goal is of growing food on Mars is, and trying to determine how effective and how much better the remediated soil is versus the unremediated soil. So then once that first cycle is done, each cycle as it goes on is slowly a reducing set of the remediators. And that's because as each cycle continues, based on the information gained from the first cycle, we will choose the best remediator, or the one that we think has the best odds, and then plant that in combination with some of the other plants, so as to get more and more data on different combinations that are potentially more and more effective based on what they can remediate to try and get a more effective scaling growth of plants. Then out of this, once the plants grow, we can then try to observe and analyze that data.
Right. So the data we collect from this experiment is twofold. First and most obvious is the quantitative data we collect. This is the soil collection rates and whether or not the plants live or die. These are numerical values that can give us an understanding of how to address the individual toxin concentrations at a Mars environment. NASA actually recently just released their choice of 6 possible landing sites. If we had a possible mission to collect concentrations of these contaminants at the site, we would be able to formulate a plan on how to address them in a future colony. But most importantly, the data that we collect from this experiment is also qualitative. Knowing and understanding how to grow these special plants, this technology, in an adverse environment such as Mars is essential for employing it on the red planet. If we can't understand, if we can't test out this ability, it's most likely will not be able to work on the red planet. The reason we have to put in all of our possible contaminants in at once and in each soil setting have that is to address the possibility of it occurring on Mars. We have to understand that dynamic of interplant relationships. It's called, the scientific term for the area in which the plants can remediate is called the rhizosphere. And so as our experiment progresses, we're dwelling more and more into what interlocking rhizospheres can accomplish on Mars. And so to continue with that, we have Trent, who's going to talk about what possible plants we might use in this experiment.
Okay, so yeah, as Owen just said, these are the plants that we've come across after many, many months of researching and going through studies. First up is our yellow mustard, or Presca junkia. We'll be extracting our sulfur and to a lesser extent lead, barium, and zinc. And so one of the main things about this is, it's an amazing phytoextractor. But other things you can use for, such as like a green manure, as in the amount of biomass it produces is like great for decomposers. So this can support like a much better nutritional environment for other plants, because that might be a huge problem that we have on Mars, is getting more nutrition to the soil. And so this plant itself is actually very good for that. Not only that, but it's also edible after the phytoremediation process, of course, for just use. And it's also a drought-tolerant plant, and it's generally a good plant to have for this kind of mission. So next up is the tarragon, which is Artemisia dracunculus, and I'll be extracting our chlorates. And so one of the main things about this one is the seed system doesn't really even exist that much. The seeds, it doesn't really spread through the seeds actually. It's more through its root system. So you end up cutting up the roots and planting them separately, and a much easier way of spreading the plant around. And so this will be edible after as well. And like yellow mustard, it's drought tolerant. And next up is our buckwheat, or Phytoparum esculentum. And I'll be extracting our lead, aluminum, and it likes a environment with less nitrogen and just lesser amounts of nutritional value, surprisingly. But like yellow mustard, it's also green manure, as in it can provide nutrients to the soil as well. And so the thing about this is its seeds are actually a substitute for wheat. So again, after the phytoremediation process, it can be used as like another way to make waffles or pancakes or muffins, anything that would require wheat. The next up is Iberian knapweed, or Centuria iberica, and we'll be extracting our iron. And the main things about this one is it's drought tolerant like the others, but it likes a much lesser nutritional environment. Like oddly enough, it prefers environments that don't have that much nutritional value to them. And common malava neglecta. And so this will be extracting our zinc. And this plant isn't too special, but it's a generally good plant to have. It's just the best for zinc, and that's what we came across. It's able to be cooked, and actually is a good substitute for okra and lettuce, and actually egg white, surprisingly, in such recipes that require egg white. And finally, we have white horehound, or Marybone vulgare, and we'll be extracting cadmium. And so the main use for this after phytoremediation process, it's also edible like all the other plants. It's just for cough drops because with all the Martian soil, it's very dusty and can end up giving you a bad cough, and so it's good to have something that can produce good cough drops. And so next up is our timetable, which is
So because of the variety in the plants that Trent just showed you, our actual timetable could potentially differ based on different growth cycles of the plants. So we've selected about 3 months as the estimate growth cycle, and then you want to take into account multiple cycles and trials per plant. And so this leads us into, you spend more money per trials, but you also gather more data. So that all leads to how much data you want to gather versus how much money you want to spend. And this leads us to projected cost.
So for projected costs, looking at these, we have the cost of the simulant, which you have an example given to you. It's about $8.99 a pound transferred over. That's $4.09 per kilogram. But if we want to do 1 kilogram of Martian simulant per plant, and we choose 75 plants, comes to about $300. Cost of hyperaccumulators themselves, with a lot of seeds and such, come to about $200. Cost of lab work is $71 per plant. At Cornell, I believe?
Yeah.
At Cornell University, they charge about $71 per testing of plants. So that wouldn't be too much. And overall, for payload cost, it's about $500 per kilogram, I believe. So that would cost about $500 because it's around 1 kilogram of seeds itself and other materials. So at that total, we have about $6,375 compared to an alternative to phytoremediation, which would be a soil washing machine, which is guaranteed surefire way to work. They're around $50,000, and they weigh 8,100 tons. And transferring over that for 500 kilograms, you'd run about 18 million just to transfer it over to Mars long term for a long term solution. So comparatively, around 18 million to 6,000, phytoremediation would be a good cost-effective solution to guarantee safety. Which leads us to our next thing.
Check, make sure it's still on.
Yeah.
The button's on the side. If it's red, it means it's on.
I guess yeah.
Now it's on.
There you go. Okay, great. So, the question of why do this experiment is a very valid one, but there are a lot of really good answers to that. For example, it's an incredibly repetitive process, so that way you can repeat it, so that way it's whatever. When you send it to Mars, you can then keep doing it over and over and over again, because no part of the experiment is dependent upon sending new payload other than the standard supplies of just operating the greenhouse. In addition, it's also a very good way of understanding how plants will grow in an alien environment. So in this case, we're trying to understand Mars, but the same sort of a procedure or general process can apply to you wouldn't want to colonize Venus, but perhaps Alpha Centauri if we get more information on that, or just the moons of Jupiter. But it's a very good stepping stone into getting more exoplanetary biology and horticulture and just trying to establish a good colony or life over there. What's more, it's also a very effective and good way of learning how to make good, clean, safe soil for growing food on there to support in the future, permanent Martian colonies that are very, very likely to, or are hopefully very likely to exist on Mars eventually. What's more, once you get the colonies up and running over there, in addition to, aside from just being a good way to get soil to grow food, you can then start working on terraforming the planet by creating a decent biosphere on there, using the plants to start making a fertile soil with good biomass, and you can then spread that around a little bit, try and get life going. But it's just a great stepping stone to getting things going in the future on trying to create a biosphere, life, and then it's repeatable, expandable. You can support colonies because of the expandable thing, you just keep converting more soil. But yeah, in the future, it's very, very stable.
So the point of our experiment, in conclusion really, is to fix this soil that we know has a very high likelihood of being toxic to plants or humans. This is a necessary first step. We cannot have any sort of Mars colony whatsoever if they are not able to produce food for themselves. and no food can be produced if the plants are dying every time you try to plant them. Our experiment is absolutely vital to NASA's mission in keeping its astronauts safe, as Ginger mentioned. If we can't ensure that the plants eaten by our astronauts are not safe to human consumption and match the regulatory standards, then we are putting them in a grave danger that could jeopardize both their lives and the lives of the thousands of people who depend on NASA. So in conclusion, because phytoremediation is such an excellent way and so excels any other attempts of remediating soil, either by using water washing or large machines, is because it fits in with our current method of creating this agriculture environment on Mars. These are plants. These plants are planted just like any other crop. You dig a hole in the ground and you put the plants in. This means that all we'll have to send up, as Ginger mentioned, are seeds. There's no extra machines. There's no extra training involved. They're just extra seeds for our possible robot machines to use when creating that greenhouse environment on Mars. So, if we want to turn the red planet into a green one, we need phytoremediation. Thank you.
Do you all have any questions?
We have time for questions, right?
Oh, yeah, you still got another,
Okay,
yeah, they got like 5, 6.
okay. I have a question about the washing machine.
Yes.
That would take care of, that would take care of the perchlorates, certainly, but it would also take care of the metals?
Yes. Soil washing on Earth is an incredibly well-established, effective method for like remediating everything from lead to aluminum, like way excessive amounts of aluminum, to all sorts of other materials that are left in the soil. They're used a lot for like when, if for example a manufacturing plant was leaching contaminants into the soil, you could then dig up all that soil, wash the soil, and you'd be left with a much denser concentration of those heavy metals. Most likely due to the difference density between the more natural nutrient-rich stuff and the toxic contaminants. From there, you can then that dense sludge or chemical sludge essentially, you can then take that to a remediating plant to dispose of it, which it's a surefire, effective way, and it leaves the soil incredibly clean by EPA standards. But it's like even on Earth, it's cost prohibitive and generally very, very labor intensive because of the amount of water and such that has to go through it.
And while it can, I believe some companies use it for like filtering gold out of the soil and stuff, kind of like a modern panning for gold sort of thing. And the thing is, it can wash through tons of soil in a short amount of time, but it is very resource intensive, which would be a very, very negative con to this situation. And we'd have to send it up in pieces, and because as a whole, 8,100 payload, an 8,100 ton payload or 16,000 pound payload is practically unfeasible as a whole. So it would require multiple missions going up and down, and that would just increase the cost.
Which also increases danger as well.
Yeah.
And in addition, a soil washing machine is also an extremely large thing, like we pointed out. And in a Martian colony, space is an extremely scarce resource as well. And also, this device, when not in use, would be completely useless, just sitting there waiting for more soil to pump out. But our plants are also, as Trent mentioned, multifunctional and can have many other uses in addition to their phytoremediating properties.
Of course, not before the phyto extraction has been completed. Otherwise, because when they are doing their extraction jobs and stuff, then they are considered just as dangerous as any other plant that's grown in there. But after all the toxic contaminants have been removed, well, not all of them, but to an EPA standard where it's below MEDIC threshold and at the lowest below the lowest observed adverse effect level, as they call it, then they can be used for like white horehound, cough drops, buckwheat, flour, etc.
And just to mention another point, the soil washing machine really has, they have its own collection system, and you would get this highly concentrated toxic sludge afterwards. It also contains, because the machine can never be truly efficient, it also contains what could be good for the plants or soil. While the plants, on the other hand, the plants that we've picked through our research hold the majority of their contaminants above their roots. So this way you can go and harvest the top part of the plant, leave the bottom part growing, and dispose of the toxic, the contaminated upper part, the contaminated stems in a safe environment. You can reclaim the water from it, and you can even burn it as a form of biofuel and reclaim the collected metals.
Ashen. It's like the difference between burning and ashen, but not ashen.
Any other questions?
Phytoremediation, in your research anyway, is it being used successfully on Earth right now?
Yes, many
Yes.
times. Like I mentioned, Tyndall Air Force Base, like that.
Tyndall.
Tyndall Air Force Base. That's the closest example to us, which is or to where we live, which is Tallahassee. So Panama City, that's like right near us, and so this is a real life example of where they successfully use plants to remediate soils that are contaminated with perchlorates. And there's many other examples that the EPA has done. They have like several resources that we can actually come across. Like there's citizen guides to phytoremediation or industry guides to phytoremediation, where you can actually implement it yourself and just do it in your own backyard, because it's as simple as just planting seeds.
There's been sunflowers grown at Fukushima, and sunflowers are another hyperaccumulator next to Fukushima, which is a giant.
Nuclear plant in Japan that with the tsunami had meltdown. The sunflowers growing next to it are very, very good at absorbing uranium, which now the sunflowers are radioactive, but the soil there is much, much cleaner. The air is a bit cleaner, so it's very, very effective at reading the target material there. But it works incredibly well.
Which might be something to keep in mind actually for a future Mars mission. If they wanted to use a nuclear power plant to increase the power available at the colony, you could plant these phytoremediating plants around it and soak up any depleted material that escaped from the system, and you could store it in a safe location far away from the base.
Honestly, it's just like it's the key to unlocking like so many other necessary and vital steps to colonizing Mars or in establishing a settlement there. And going back to your initial question, is this working? Yes, it is. My godfather is working in Ohio and he works with several phytoremediation experts, which is where we were able to get some information from regarding our experiment and procedure-wise. And it works under bridges and stuff, and in places that people are like more likely to be found in, and his job is to keep people safe, and he says it works surefire.
Give us one specific example of growing like willow trees that the diameter he gave us was probably about this yay big around, that as he described them, little sticks, and you can plant them in different places with contaminated water well beds, and they will soak up an incredibly large amount of water that is contaminated with, I think he said, lead. And you can then like harvest the trees or whatever and replant them, and they will soak up, because the trees can make an incredible amount of biomass, they can store an incredible amount of lead, so they can then soak up a large amount of lead from the soil and water over time and block it away, so that way it doesn't spread and contaminate other areas.
But those willow trees have had taking a longer amount of time, so that's why we didn't end up using it. Because they also have a lot more water intake, and so that's why we chose littler, smaller plants like Indian mustards or tarragon, which are much smaller and use less water.
We're good.
All right,
Thank you guys.
Thank you very much.